Hello everyone, so this is the second video of our self-paced learning material for lecture 7. In the previous video, we've seen that most reactions are carried out under constant pressure conditions. Thus, the heat of reactions are also called the enthalpy of reaction, which in reality is the change in enthalpy occurring during a chemical reaction. So in the second tutorial, we will look at how we can determine the value of the change in the enthalpy in a chemical reaction. The change in enthalpy in a chemical reaction can be determined in three ways. First involves combining certain thermochemical equations, which we will discuss in a while, to yield the reaction of interest. We do this using the Hess law of heat summation. A second way is to carry out the reaction in a calorimeter, and we can also determine the change in the enthalpy from the absolute standard enthalpy data. We will start our discussion by looking at thermochemical equations. So what exactly are thermochemical equations? Thermochemical equations are basically balanced chemical equations that describe the following aspects. First, it involves a balanced reactions with physical states of substances shown for reactants and for the products. Thermochemical equations can also involve fractions as numerical coefficients. And whenever we write thermochemical equations, we usually indicate the temperature and the conditions of the system. Now consider the following example. In the first reaction, 1 mole of hydrogen reacts with half mole of the oxygen to form 1 mole of water vapor. This has a corresponding change in enthalpy of negative 241.82 kilojoules. In the second reaction, 2 moles of hydrogen reacts with 1 mole of oxygen to form 1 mole of water in vapor phase. This has a corresponding change in enthalpy of negative 483.64 kilojoules. Now, recognize that these two reactions refer to two distinct reactions even though the same substances are involved. This example actually relates the property of enthalpy, but it is an extensive property. It means that its magnitude is directly proportional to the amount of reactants consumed in the reaction. Another behavior of thermochemical equations is that if both sides of the equation are multiplied by the same factor, the heat of reaction is also multiplied by the same factor as shown in the following example. The second property of thermochemical equations that we need to know is that the enthalpy change for a reaction is equal in magnitude but opposite in sign to the enthalpy change for the reverse reaction. Consider the example shown above. Reversing the first reaction to give the second reaction will simply reverse the sign of the change in enthalpy of this first reaction. This is actually expressed by the Laplace principle, which states that the heat of the forward reaction is equal but opposite in sign to the heat of the reverse reaction. As what we've seen in the past two examples, in addition to the number of moles and molecules of the reactants and products that are present in any chemical equation, sometimes you can also have the enthalpy of the chemical equation shown on the right. Using this information, we should be able to determine how much heat will be released or absorbed depending on how much product or reactant we have. We will illustrate this one in our next example. The thermite reaction is highly exothermic, and the reaction is given in the slide. We are asked how much heat is liberated when 36 grams of aluminum reacts with excess ferric oxide. So based from the reaction, we know that negative 848 kilojoules is stoichiometrically equivalent with 2 moles of aluminum. We can simply carry out a factor label approach to solve for the heat that is liberated as shown above. This gives us a value of negative 565 kilojoules of heat. Now you can also answer the following questions as additional materials for your learning. In this slide, we will look at how we can determine the change in enthalpy of a chemical reaction using the Hess law of heat summation, or simply Hess law. The Hess law states that the change in the enthalpy for any chemical reaction is constant, whether the reaction occurs in one step or in several steps. Now, try to consider the figures shown on the right. Delta H1 is the change in the enthalpy from A to B, which is pathway 1, which is the most direct route with no intermediate stages. We can also go from A to B through an intermediate step C. If each step has a corresponding delta H, then delta H1 is equal to delta H2 plus delta H3. We can also consider another pathway involving two intermediates, D and E, with each step having a corresponding delta H. So in this case, we can say that delta H1 is equal to delta H4 plus delta H5 plus delta H6. In general, there is no limit in the complexity of the Hess law cycle as long as A and B are constant. To apply Hess law, let us consider the following problem. We're given three reactions with their corresponding change in enthalpy, and we are asked to calculate the final change in enthalpy of the reaction shown in red. For this discussion, the original equation will be shown in blue, and the target or the final equation will be shown in red. Now, any changes in the thermochemical equations will be shown in purple. To calculate using the overall change in the enthalpy using the Hess law, we can treat thermochemical equations algebraically to obtain new equations. Consider the first reaction. Recognize that HCl has a stoichiometric coefficient of 2 in the final equation. This means that we need to multiply the given equation, shown in blue, with a factor of 2 to give the revised thermochemical equation, which is shown in purple. Recognize that this reaction needs to be reversed so that the C and the H in the product side will be used to cancel the same elements in the third equation. Notice that the delta H changes in sign as the equation is reversed. Now, for this reaction, we leave the reaction as it is because the product side already contains the dichloromethane. Now, combining all the revised thermochemical equations, the terms common to both sides of the equations are cancelled. Ultimately, the delta H is equal to negative 265.9 kilojoules per mole. Now you can try to answer the following problem and you must be able to get a change in enthalpy of negative 1075 kilojoules. You can also try this problem to calculate the enthalpy of esterification. So I hope everyone knows the reaction of esterification. So for you to solve this problem, you have to write the chemical reactions first.